This video is sponsored by Engineered Labs. Imagine a metal so hidden in your everyday life that most people have never heard its name. Yet it plays a critical role in some of the most advanced technology on Earth. Ytterbium is such a metal, a little-known element quietly enabling ultra-precise atomic clocks, lasers and even quantum computers. We will return to a tiny Swedish village and discuss its unique properties and cutting-edge applications that make it the secret hero behind world-changing innovation. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. And if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another element again. So what we have here looks like a quiet shard of moonlight, silvery white, sometimes with a faint golden tint when freshly cut. It's soft, malleable and ductile. You can scratch it with a knife and bend a smaller bar without snapping it. In air, it tarnishes slowly, forming a thin coat of ytterbium oxide that dulls the shine, but helps protect the metal underneath. In a lump, it behaves politely, but grind it up and it shows its wilder side. Fine ytterbium shavings can ignite in air, and the metal reacts with water. Slowly when cold, faster when hot, to make hydrogen gas and a slippery hydroxide. And that brings us to the question, can you lick it? Well, in this case, I would say no. And the periodic licking table seems to be really off here. Ytterbium isn't a snack, and your mouth is a bad reaction vessel. While a solid chunk of the pure metal isn't as notoriously poisonous as mercury, lead, or arsenic, ytterbium compounds, salts, can be harmful if swallowed and may irritate skin and eyes. Now, the powdered metal is, like mentioned, a fire hazard, and even the bulk metal can react with moisture, releasing hydrogen. In labs, ytterbium is often kept sealed under oil or inert gas to stop it from reacting. Clear hints, it doesn't belong on your tongue. So can you lick it? Hard pass, no, don't do it. Now the next part seems like a little bit of a déjà vu. The story of ytterbium begins in the late 19th century with a mineral and a village. In 1878, Swiss chemist Jean-Charles Galissard de Marignac was studying a mineral called gadolinite, a dark rock rich in unusual metals. When he noticed something new, he managed to separate a new earth, old terminology for oxide, from an existing rare earth oxide known as erbia. Now, sensing that he found a new element, Marignac named this new oxide Ytterbia, after the place where the mineral has been found, Ytterby, a quiet village in Sweden. Now, Ytterby might seem obscure, but as we found out in many of the other episodes about the Lanthanides, it's famous in chemistry. No fewer than 4 elements are named after it: yttrium, terbium, erbium, and ytterbium. The name Ytterby itself simply means outer village in Swedish, but in science it has become legendary. If you want to know more about ytterbium's discovery, by all means go back to the lutetium episode where we will discuss how ytterbium was further discovered. So what kind of an element is ytterbium? Ytterbium has a chemical symbol Ib and atomic number 70, which means that an atom of ytterbium has 70 protons in its nucleus. On the periodic table, ytterbium sits among the group of elements known as the Lanthanides, or rare earth elements. It's actually the 14th element in the Lanthanide series, making it the penultimate, second to last, lanthanide. These lanthanides are often found clinging together in the same ores and have similar chemical behavior, which is why separating them, as Marignac and others had to do, is so challenging. In terms of atomic structure, ytterbium is interesting because of its electron configuration. It has a completely filled 4f electron shell, often written as this, and this closed shell configuration makes it a bit different from many of its other lanthanide cousins. Now, as we will discuss, this contributes to some of ytterbium's physical properties, like a relatively low melting point, and also allows ytterbium to sometimes use an uncommon oxidation state in its chemistry. Now, ytterbium is not something you encounter in pure form in daily life. It's not a coinage metal or building material, so our sense of it comes mostly from lab observations. One notable thing, ytterbium is quite dense, but not extremely so. Its density is about 6.97 grams per cubic centimeter, around 7 times the density of water. Now to compare, iron's density is about 7.9 grams per cubic centimeters and copper is about 8.9 grams. So ytterbium is a bit lighter than those common metals. It's heavier than aluminum 2.7 or titanium 4.5. But for a heavy rare earth element, ytterbium is actually on the lighter side. The reason is that closed shell electron configuration we mentioned. It influences how tightly packed the atoms are in the metal structure. Ytterbium's basic vital stats include a melting point of about 824 degrees Celsius, 1515 degrees Fahrenheit, and a boiling point of around 1196 degrees Celsius, 2185 degrees Fahrenheit. Now notice something interesting here. The difference between the melting and boiling point, the liquid range, is only roughly 370 degrees Celsius. That's actually a very narrow liquid range for a metal. In fact, ytterbium has one of the smallest temperature windows as a liquid for any metal. Now for comparison, most metals stay liquid over a much bigger temperature interval before boiling off. This narrow range is another side effect of ytterbium's filled electron shell and weak bonding. It doesn't take extreme heat to go from solid to liquid to gas compared to many other metals. Another unusual thing, ytterbium has allotropic forms. Allotropes are different structural forms of an element depending on conditions, like how carbon can be graphite or diamond. For metals, allotropes often mean different crystal structures at different temperatures or pressures. Ytterbium has 3 allotropes named alpha, beta, and gamma. The alpha form exists at a low temperature, below about minus 13 degrees Celsius. It has a hexagonal crystal structure and a density around 6.9 grams per cubic centimeter. The beta form is stable at room temperature, so this is what ytterbium usually is under normal conditions. It has a face-centered cubic FCC crystal structure and a density of about 6.97 grams per cubic centimeter. This is the form most commonly observed in the lab. Last but not least, the gamma form appears at higher temperatures, above roughly 795 degrees Celsius, under ambient pressure. It has body-centered cubic BCC structure and a lower density, approximately 6.57 grams per cubic centimeter. Switching between these forms is influenced by temperature and also by pressure or stress. In fact, ytterbium's behavior under pressure is very intriguing. Under extremely high pressures, the metal undergoes electronic changes that affect its conductivity. At about 16,000 atmospheres of pressure, a condition far beyond everyday experience, but reachable in lab instruments, ytterbium's electrical conductivity drops. It actually starts behaving more like a semiconductor than a metal. Its resistance increases dramatically to a certain pressure, approximately 39,000 atmospheres. Then, if you pressurize it even more, around 40,000 atmospheres, its resistivity suddenly plummets back down to a very low value, about 1/10 of its normal value, almost like it becomes a good conductor again. These strange jumps are related to ytterbium's electrons rearranging under pressure. Scientists study such behavior to understand how electron shells respond when squeezed. Ytterbium provides a useful example because of that easily rearranging F-shell. Magnetism is another property where ytterbium is a bit of an outlier among its peers. Many lanthanides show magnetic order, like gadolinium, is a strongly ferromagnetic. Others are anti-ferromagnetic at low temperatures. Ytterbium, however, is mostly paramagnetic under normal conditions, meaning it is only weakly attracted to magnetic fields and doesn't maintain magnetism itself, at least above very low temperatures. In fact, above about 1 Kelvin, which is essentially all everyday temperatures, ytterbium remains paramagnetic. And interestingly, the low temperature alpha allotrope of ytterbium is actually diamagnetic, slightly repelled by magnetic fields. So unlike a lot of its lanthanide cousins, you won't get strong magnet behavior from ytterbium in a typical scenario. Ytterbium is quite electropositive, meaning it readily gives up electrons to form positive ions. If you put a piece of ytterbium in water, it reacts slowly with cold water and a bit more quickly with hot water. The reaction produces ytterbium hydroxide and hydrogen gas, a typical behavior from metals like magnesium and calcium as well. Now, it doesn't fizz violently in water like sodium or potassium, but over time you'd see bubbles of hydrogen on the metal as it corrodes. In acids, ytterbium reacts much faster. Drop a bit of ytterbium metal into hydrochloric or sulfuric acid and it will dissolve, releasing hydrogen gas and forming ytterbium salts in the solution. This is standard for an active metal. Acid plus metal is hydrogen gas plus salt. In compounds, ytterbium most commonly exhibits a +3 oxidation state. That means in ionic compounds, you'll usually find ytterbium 3+ paired with some negative ions. For example, ytterbium 3 oxide is each ytterbium gives up 3 electrons to oxygen. And ytterbium 3 chloride shows like this. Now, ytterbium might be obscure, but it's not completely absent from nature. In fact, if you have a shovel and go digging in certain parts of the world, you might find trace amounts of ytterbium in the soil or rocks. The average abundance of ytterbium in the Earth's crust is about 3 milligrams per kilogram of rock. Put it in another way, for every million grams of rock, you might find 3 grams of ytterbium mixed in, on average. That makes it less common than more familiar metals, like copper or zinc, but among its lanthanide neighbors, it's actually not the least abundant. Interestingly, there is a pattern in the periodic table called the Odo-Harkins rule. Elements with even atomic numbers tend to be more abundant than their odd-numbered neighbors. Ytterbium, atomic number 70 even, is significantly more abundant than either thulium, 69, or lutetium, 71, which flank it on the table. So despite being rare, ytterbium is more plentiful than some of its immediate peers. Ytterbium is almost always found mixed with other rare earth in mineral deposits. A few minerals known for containing ytterbium and other lanthanides are monazite. This is a reddish-brown phosphate mineral that is a major source of many rare earth elements. Monazite is mined primarily for cerium, lanthanum, and neodymium. But when they process it, they can also extract small amounts of ytterbium and others. Xenotime, a yellow-brown phosphate mineral that usually contains yttrium. Xenotime often has a good dose of heavy lanthanides like ytterbium and gadolinium. And then we have euxenite and gadolinite. These are complex oxide minerals rich in rare earths and other elements like niobium and titanium. Historically, the very mineral that sparked ytterbium's discovery was gadolinite from the Ytterby mine. Gadolinite is a silicate that contains yttrium, ytterbium, etc. However, these days, gadolinite is not a primary commercial source. It's more a historical footnote, whereas monazite sands and other broad rare earth ores are the main sources. Now, the main mining areas for rare earths, including ytterbium, are China, currently the largest producer of rare earth elements in general. Southern China has clays and minerals rich in heavy rare earth, like ytterbium and gadolinium, etc. The United States, the Mountain Pass mine in California was historically a big rare earth source, mostly light lanthanides, but heavy ones can be byproducts. The US also has some other deposits and can produce small quantities. Brazil and India, they have monazite sand deposits, often as byproducts of other mining, where rare earth metals can be extracted. Also Sri Lanka and Australia are on the list. It's estimated that the worldwide ytterbium reserves, the amount reasonably certain to be in the ground and potentially extractable, are on the order of 1 million tons of ytterbium, which sounds like a lot, but remember, it's usually spread out thinly in large volumes of ore. Annual production of ytterbium is relatively small, roughly 50 tons per year globally. Now, fun fact, ytterbium has even been found beyond Earth. A report once indicated the presence of native ytterbium metal in moon rock samples in the lunar regolith. This doesn't mean that there are chunks of pure ytterbium on the moon, but trace elements like ytterbium are indeed present in lunar soil from meteor bombardment and primordial solar system material. Now, getting pure ytterbium is not as simple as digging up a shiny nugget. Like most rare earth elements, ytterbium hides inside minerals such as monazite and xenotime, where it's slightly mixed with other lanthanides. To separate it, miners first crush the ore and then treat it with strong acids or hot alkalis, which dissolve the rare earth elements into a complex soup of ions. The tricky part is pulling them apart, since lanthanides behave almost the same chemically. Now, modern industries use solvent extraction, where organic liquids selectively grab one element at a time, or ion exchange resins, which act like molecular sieves. Because ytterbium can exist in a rare +2 state, as well as the usual +3, chemists also used selective reduction methods, such as reacting it with sodium amalgam to isolate it from its neighbors. Once separated, ytterbium is usually converted into compounds like ytterbium oxide or ytterbium chloride. To obtain pure metallic ytterbium, these compounds are reduced with more reactive metals like calcium or lanthanum in a vacuum furnace. The ytterbium then vaporizes at relatively low temperatures. Its boiling point is only about 1200 degrees Celsius, one of the lowest among rare earth metals, and condenses as shiny ingots or crystalline pieces. The process is long, costly, and complex, which is why worldwide production is only about 50 tons a year, even though the Earth's crust contains over 1 million tons of ytterbium in total. So let's talk about the applications. First and foremost, let's address the headline: ytterbium's role in ultra-precise atomic clocks. Atomic clocks are the gold standard for keeping time. They are what define the second and keep GPS satellites and telecommunications synchronized. Now, for decades, the world's official timekeeping has been based on cesium atomic clocks, using the element cesium. But ytterbium is at the forefront of new generation of even more precise clocks, often called optical lattice clocks. In 2013, researchers at the US National Institute of Standards and Technologies, NIST, announced that a pair of experimental ytterbium atomic clocks had set a record for stability. Stability here means how consistently each tick of the clock matches with the next tick. The ytterbium clocks were so stable that their ticks only varied by less than 2 parts in a quintillion. That's this number, an unimaginably tiny fraction. To put that into perspective, if one of these clocks had been running since the Big Bang, 13.8 billion years ago, it would be off by less than a single second today. That's how precise they are, measuring time with accuracy that stretches across the entire age of the universe. Now, how does this work? Well, the ytterbium atomic clocks are a type of optical atomic clock. Traditionally, atomic clocks like cesium clocks use microwaves to probe atomic transitions. Optical clocks use visible light, which has a much higher frequency. Here's a simplified picture of the NIST Ytterbium clock operation. Now, first of all, they gather about 10,000 ytterbium atoms in a vacuum chamber and use lasers to cool them down to an extremely low temperature, only a few microkelvins above absolute zero. At such a low temperature, the atoms move extremely slowly, which is good for precision. These ultra-cold ytterbium atoms are then held in place by another set of lasers, forming what's called an optical lattice. You can imagine an optical lattice as a grid or an egg carton made of light. Lasers interfere in such a way to create a standing wave with regions of light and dark, forming little pockets that can trap atoms. The lattice holds the ytterbium atoms neatly in place, isolating them from outside disturbances. Now, ytterbium atoms have electrons that can jump between specific energy levels if they absorb the right color frequency of light. One particular transition in ytterbium between two energy states of the atom is used as the clock's pendulum. A very stable laser is tuned to exactly the frequency that causes the ytterbium electrons to transition. This frequency is about 518 trillion ticks per second, or 518 terahertz, which is in the optical range of light. Each tick of the clock corresponds to a certain number of oscillations of that laser lights that keep the ytterbium atoms excited. Because optical frequencies are so high, you can divide time into much finer slices than with microwaves. It's like having an ultra-fine ruler for time. Now, by probing the atoms and adjusting the laser to stay in sync with the atomic transition, the clock achieves an extremely regular output of time pulses. The reason these clocks are so stable, especially the lattice clock with thousands of atoms, is that by averaging over many atoms simultaneously, a lot of the random noise cancels out. If one atom jitters, the others keep the beat. The result is a phenomenal averaging that yields incredibly consistent after even a short time of measurement. Now, what is truly mind-blowing is the potential of these clocks. They're so precise that scientists say they could detect minute effects like gravity influence on time. According to Einstein's theory of general relativity, time runs slightly slower in stronger gravity, like at lower elevations closer to the Earth's mass, and faster in weaker gravity at higher elevations. Now, with two Ytterbium clocks, one just a few tens of centimeters higher than the other, you would actually measure the difference in ticking rate due to the gravity difference, effectively measuring the warping of space-time on a tabletop scale. In fact, such clocks could be used like geological sensors by observing time dilation. They might help survey the shape of the Earth's gravitational field, revealing hidden ore deposits or changes in the planet's crust. These Ytterbium clocks represent the cutting edge of timekeeping, and they are currently experimental but inching towards practical use. They won't be in wristwatches or keeping train schedules. We don't need nanosecond precision for daily life, but they could redefine the second in the future or be used in scientific observatories and GPS upgrades. The phrase, "the secret metal behind ultra-precise atomic clocks," is well earned. Without Ytterbium's specific atomic properties, the convenient energy transition, the ability to be laser-cooled, etc., we wouldn't have this powerful tool. Now, from the esoteric realm of atomic clocks, let's shift to something more down-to-earth: stainless steel. One of the more practical uses of Ytterbium is as a dopant, an additive, in certain alloys. Notably, some stainless steel. Metallurgists have found that adding a tiny fraction of Ytterbium, or similar rare earths, to steel can help refine the grain structure of the metal, and it improves its mechanical properties. If you have ever undergone laser surgery, used a laser pointer, or observed industrial laser cutters, you might have indirectly benefited from Ytterbium. Ytterbium-doped lasers are a big deal in the laser world. Specifically, Ytterbium is widely used to dope the active medium of a solid-state laser and fiber lasers. Now let's talk about how that works. Well, many lasers consist of a host metal, like a crystal or a glass fiber, that is doped with a small amount of an active ion, which actually produces the laser light. Ytterbium ions are exactly for this purpose. For example, the YAG laser, the yttrium aluminum garnet, which we've talked about in our aluminum episode, is a crystal often used in solid-state lasers. YAG, being a famous one for its green laser output, replace neodymium with Ytterbium and you get YAG. Ytterbium lasers typically emit in the infrared around 1030 to 1100 nanometers of wavelength. You also have Ytterbium fiber lasers. In fiber lasers, the core of an optical fiber is doped with Ytterbium ions. Pump lasers around at 940 nanometers near infrared, excite the Ytterbium, and it can then laze at 1030 to 1100 nanometers. Ytterbium fiber lasers have become extremely popular for industrial cutting, welding, and even telecommunications because they can be made very powerful and efficient. Now, why would we use Ytterbium specifically? Well, it has a relatively simple energy level scheme with a small quantum defect. This means the difference in energy between the pump light and the laser output is smaller, which translates to less wasted energy, heat, and more efficient conversion of pump light to laser light. Ytterbium lasers can achieve high efficiencies. Over 60% of the pump energy can turn into laser energy, which is huge for lasers. They also tend to have long operational lifetimes, and they can be pumped by reliable laser diodes. Additionally, yttrium-doped materials can often be run at high doping levels and high powers without some of the issues that other dopants have. Now, high power outputs, especially in fiber lasers, yttrium doping has led to multi-kilowatt continuous lasers that can cut through thick metal plates or do precise machining. Short pulse generation, yttrium doped lasers can be designed to produce ultra short pulses. Picosecond or femtosecond pulses for applications like laser cutting, medical surgery, or scientific research, for instance, studying fast chemical reactions. And last but not least, its reliability. Yttrium lasers are relatively low maintenance and stable, making them workhorses in the industry. Another frontier technology benefiting from Ytterbium is quantum computing. In particular, one leading approach to quantum computers used trapped ions as quantum bits, qubits. Ytterbium has emerged as the favorite choice for some of these systems. Now, how does that work? Well, if you take a single ytterbium atom and strip one electron off, you get a ytterbium plus ion. Ions can be held in electromagnetic traps using electric fields and magnetic fields to confine them in space. Researchers at places like IonQ and various university labs trap these ytterbium ions in a row and use laser beams to manipulate their quantum states. Again, why ytterbium ions? Well, they have the energy level that are convenient for defining qubit states. Two hyperfine levels of the ytterbium ion can serve as the 0 and 1 states of a qubit. Now, they can also be manipulated with lasers to perform quantum logic operations. For example, lasers can be used to induce interactions between ions, entangling them, or to read out their state by causing them to fluoresce. Ytterbium ions, especially the Ytterbium-171 isotope, have relatively long-lived qubit states and can be initialized and detected optically with high fidelity. Now, in practice, quantum computers with trapped ytterbium ions involve shining carefully tuned laser pulses to do things like Mulmer-Sørensen gate, which entangles multiple ion qubits by making them wiggle in unison through their mutual electrostatic repulsion. Ytterbium ions have proven to be a reliable platform for some of the most advanced quantum computer demonstrations to date. While this is all very cutting edge and experimental, it's another place where this unassuming element plays a starring role. Now, ytterbium even finds its uses in the medical and industrial world through one of its isotopes. Ytterbium-169 is a radioactive isotope of ytterbium not found naturally, but produced in nuclear reactors by bombarding ytterbium with neutrons. It has a half-life of about 32 days and emits gamma rays. Now, what is it good for? Well, Ytterbium-169's gamma rays are relatively low in energy compared to, say, cobalt-60, but high enough to penetrate some materials. This makes Ytterbium-169 a handy source for portable X-ray machines and radiography. In places where electricity or large X-ray equipment isn't available, or for imaging small objects, a tiny sealed capsule of Ytterbium-169 can act as a source of penetrating radiation. For example, it can be used to take X-ray images of mechanical parts, pipes, or in medical settings to image tissue, similar to how we use X-ray machines. The image from an Ytterbium-169 source are comparable to X-rays of about 250 keV energy. In nuclear medicine, Ytterbium-169 has been explored for brachytherapy, a treatment where a radiation source is placed close to or inside a tumor to kill cancer cells. We've heard this before in the lutetium episode. Its gamma radiation can destroy tumor cells in a targeted way. One benefit of Ytterbium-169 is that the gamma rays have a shorter range than some of the other isotopes like Iridium-192, potentially meaning less damage to healthy tissue beyond the target. However, Ytterbium-169's relatively short half-life means that it has to be used quickly after production and replaced often. It's one of those specialized tools, not as common as technetium-99m or cobalt-60 in medicine, but definitely valuable in certain scenarios. Next time you check the time on a GPS-enabled device, consider that far beyond your view, maybe in some national lab or satellite, ytterbium atoms are vibrating with perfect regularity to keep that clock on point. Ytterbium might be the secret metal to the public, but in the realms of science and technology, it's a quiet powerhouse ensuring our clocks to run precise, our lasers are strong, and our future innovations have a solid foundation. Who knew that the outer village element Ytterbium would be so far from its humble origins? Now you do, and hopefully you'll appreciate this hidden gem of an element that makes our modern world a little bit more precise and bright. Now, have you ever wanted to hold the elements of the universe right in your hand? Now, at Engineers Lab, science isn't just something you read about. It's something you can see, touch, and display. In fact, these are the beautiful cubes that you see in our videos every single week. With their Element Cubes subscription, you'll receive a beautifully crafted acrylic cube each month, containing a real sample of a different element from the periodic table. Now, from the gleam of titanium to the deep glow of europium, these cubes turn chemistry into something you can actually collect and admire. Each one shows the elements, symbol, and the atomic number, like having a tiny museum piece shipped right to your door. Now, whether you are a student, a teacher, or just somebody who loves science, this is your chance to build your own periodic table piece by piece, like we have been doing for the past 1.5 years. Imagine lining up all the elements on your desk or shelf, a beautiful display of nature's building blocks delivered monthly. So if you've ever dreamed of exploring the hidden world of elements, check out Engineered Labs' Element Cube subscription. You can find a link in the description where you get a 10% discount if you use the promo code. It's science you can hold. Now, we would really like to thank also the members that support our channel. Thanks for doing this, we really appreciate you. Now, if you think we missed anything, tell us in the comments, and if you want to know more about another rare earth element that secretly powers our world, make sure to watch this episode about samarium next.